Students, next we are going to discuss the second application of Amperes Circuital law, and we are going to find the magnetic field produced by a solenoid using Amperes Circuital law. Now you all know what is a solenoid. You have studied in lower class. It is actually a coil of insulated wire. If you have a wire, you make into coil, you will get a solenoid. And when current passes through a solenoid, it produces magnetic field. So a solenoid can also be called an electromagnet. Now, in the previous class, we studied the pattern obtained by a circular coil of wire when current passes through it. I told you, if we have a circular coil, the field lines near to the coil will be concentric circles, and as we move towards the center of the coil, this is a coil of wire carrying current. At the ends, means towards near the circular coil, we have concentric circle patterns of magnetic field, and towards the center we get almost parallel lines. Now imagine I am bringing a second coil and I am placing near to the first one. What will happen? It will also produce a similar type of magnetic field. But the thing is, no two field lines cross each other. We have studied in 10th standard. Never two field lines will cross each other. Why? If they are crossing at that particular point, field will show two directions. So in solenoid, I told you there are n number of turns. We are taking a wire and making into coil n number of turns. So at the end, the magnetic field will align in this pattern. Now, if you can see, this is a coil of wire. I am keeping my coil of wire like this. Okay, so what happens? Current is coming out of the coil, then it is going into, then coming out, going into. This is my solenoid. And I obtain a pattern, a magnetic pattern like this. Now, if you look into the diagram, you can see outside the coil, means if this is my coil, outside region we get a feeble, or we can say almost a zero magnetic field. Very feeble magnetic field will be produced outside the coil, and towards the center of the coil you can see many number of field lines, which means field is stronger at the inner portion of in the center of the coil, and the field is aligned in parallel lines. Okay, now this is the view of the field pattern outside. So this is the dot and cross represents coil coming out of the board, going into the board, coming out of the board, going into the board, and field patterns are outside the coil. It will be concentric circles, but compared to the center or the inner portion, you can see lesser number of field lines, which means very weak field, or we can say negligible field, while inside it is a very strong field. Now, you know, if you have a magnet, definitely it will have a north pole and a south pole. I want to find out which is the north pole of my magnetic field. Just take your solenoid, close it with your right hand, then the fingers represent here, the fingers represents the direction of the current. So it is coming out, going inside, and my thumb represents, the direction of my thumb represents the north pole. So this is my north pole. Okay, now we are going to use Amperes Circuital law to find out what is the field produced by a solenoid. For that, what I am going to do, I am going to construct a imaginary closed loop which is symmetric to my magnetic field, and in our case, it will be a rectangle. Okay, so this represents my imaginary surface or my Amperian loop, and the straight lines represents my field. Okay, so and the dotted rectangle represents my imaginary Amperian loop. I have named my Amperian loop as A, B, C and D. Now what is Amperes Circuital law saying? Amperes Circuital law says the line integral of magnetic field over a closed surface B dot dl is equal to mu 0 times the current passing through the closed surface. Now my surface I have divided into 4 parts. So I am going to split the line integral into 4. Okay. First we will take from A to B. This is my line integral. So integral from A to B, B dot dl plus from here to here, because my loop is like this. Integral from B to C, B dot dl plus, next my direction is towards D. So, integral from C to D, B dot dl plus, again coming down, integral from D to A, B dot dl is equal to integral of the closed surface B dot dl, which means I have separated my closed loop into 4 parts, that is integral from A to B, directions from A to B. So, integral from A to B, B dot dl plus integral from B to C, B dot dl plus integral from C to D, B dot dl plus integral from D to A, B dot dl. We are going to find out the value for each case and substitute. Okay. First, let us take the case from D to A and C, B to C, these 2 points, these 2 sections. Okay. Now, integral from D to A, B dot dl, and I am going to take integral from B to C, B dot dl, which is equal to what? Integral B dl cos theta. So, my next step is to find out what is angle theta. Now, just look into here. See, my field is in this direction. In both the cases, my field is in this direction. But what is my line integral dl direction? It is perpendicular. Dl is perpendicular in both the cases to the magnetic field. So, what is angle theta here? Theta is equal to 90 degree. Field is in this direction, my line integral, my element dl is perpendicular. So, theta is equal to 90 degree, which means B dl cos theta. What is cos 90? 0. So, B dl cos 90 is equal to 0. So, in both the cases, the value is equal to 0. Why? Since B and dl are perpendicular, theta is equal to 90 degree. Okay. Next, we are going to consider the case from line integral from C to D. Now, I told you the field outside, if you look into the loop, there is no field here, which means field outside the loop is 0. So, what happens? Integral from C to D, B dot dl is equal to 0, is equal to 0. Why? Since B is 0 outside our Amperian loop. Okay, now let us take the next case. What is integral from A to B, B dot dl? Look here, from A to B, this is my dl, my magnetic field, B is in this direction, which means both are parallel to each other. So, theta is equal to 0 degree. So, we get integral from A to B, B dot dl is equal to integral B dl cos 0, which is equal to integral B dl. Now, we are going to integrate. So, integral from A to B, B dot dl is equal to integral B dl. If you look into the diagram, you can see field inside the solenoid is parallel and uniform, which means it is a constant field. So, we can take B outside, we get B integral A to B dl, and dl is the length of the Amperian loop. So, it is equal to B into L. Okay. Now, what did Ampere say? Integral of B dot dl for a closed surface is equal to the total current passing through the surface. So, I can write this as BL is equal to mu 0 times the current passing through the surface. Now, You know, solenoid means it consists of n number of turns or n number of coils, and through this n number of coil current will be passing. So what will be the total current in the solenoid? N into I, isn't it? So we can write this as mu n into I, or magnetic field B is equal to mu 0 I n divided by if this is the total number of turns, where capital N is the total number of turns in the solenoid. Imagine I'm going to divide my solenoid into small parts. So where small letter n, this is the difference, capital N represents the total number of turns, whereas small letter n represents the number of turns per unit length. Number of turns per unit length. So capital N is equal to small letter n into L. So this equation can be written as B is equal to mu 0 I, instead of capital N you can put small letter n, L divided by L. You will get mu 0 n into I. Don't forget, capital N is the total number of turns in the solenoid, whereas small letter n is the number of turns per unit length. Now experimentally it has been also proved that if you want to find out what is the field at the end of the solenoid, at the end point, the value of magnetic field will be equal to mu 0 Ni divided by